Okay, so again, good morning. So today we will start. We'll start by continuing from where we stopped yesterday. Okay, yesterday we stopped at yesterday what we learned is that about how is it that we can emit electron. Okay, how is it that we can produce a cathode ray, which is an electron beam through thermionic emission. Okay, and we can demonstrate that by using the apparatus called the thermionic diode. And then after that, we want to study and understand more about the characteristic of the cathode ray. So we investigate what will happen to the cathode ray if we expose the cathode ray to electric field and magnetic field. So we do that by using the reflection tube and Maltese cross tube. Okay, so today we want to continue. Okay, so here in the note, okay, here in the note, this is basically the same thing that what we discussed yesterday. What happened to the cathode ray in the diffraction tube? What happened to the cathode ray in the Maltese cross tube? Okay, so today we continue after that. What is it that we want to learn today is how to find the velocity of an electron in a cathode ray tube. Okay, basically we know that when we produce a cathode ray, what happens is the electron is repelled by the cathode and attracted by the anode. So the electron will accelerate from the cathode to the anode. Okay, so I want to stress that the cathode, the electron undergo acceleration, acceleration from the cathode to the anode. That means the velocity of the electron at the cathode is 0 meters per second, and then as the cathode repel and the anode attract, so the electron accelerate, getting faster and faster and faster, and achieve the maximum velocity when the electron reach the anode. So that is what we want to calculate, the maximum velocity. What is the maximum velocity of the electron? Okay, after acceleration, when the electron reach the anode, how much is the velocity? Okay, all right. So, okay, so to find out the let me continue on top here. Okay, so like what we discussed just now, the electron undergo acceleration and the electron will reach the maximum velocity when it reach the anode. So we want to find out this maximum velocity is how much. Okay, all right. So how do we find the maximum velocity? You see, we can find the maximum velocity from the kinetic energy that the electron gain when the electron accelerates from the cathode to the anode. So if we find out how much is the kinetic energy, we can find out the velocity, because the kinetic energy can be calculated with the equation of half mv squared. So as you can see here, there is a velocity here. So that means if we know the mass of the electron and we know the kinetic energy that the electron gained, then we can calculate the velocity or the maximum velocity of the electron. So now the problem is how much is it that the kinetic energy of the electron after accelerate. Okay, so we can find out the amount of energy that the electron gain from the potential difference. Okay, from the potential difference between the cathode and the anode. Okay, how much is the potential difference? If you still remember, potential difference is the amount of work done to move every 1 coulomb of charge from one point to another point. Right? The amount of work done to move every coulomb of charge from one point to another point. So for example, if the potential difference is 1 volt, then that means 1 joule of work is done to move 1 coulomb of charge from one point to another point. So if you do the work of 1 joule to move the 1 coulomb charge from one point to another point, what happens is the work done is 1 joule. So what is work done? Work done is you use energy or you convert and transfer energy. So what happens here is that if the potential difference between cathode and anode is 1 volt, so it means that the potential difference between the cathode and the anode is do the work of 1 joule to push the 1 coulomb of charge from the cathode to the anode. So that means that at the end, the 1 coulomb of charge will gain the energy of 1 joule. Okay, the 1 coulomb of charge will gain the energy of 1 joule when the 1 coulomb of charge moves from cathode to the anode. So when the 1 coulomb of charge gain the 1 joule, what happens to the 1 joule? The 1 joule of energy will be converted into kinetic energy. So that means this work done is the amount of kinetic energy that the electron or the 1 coulomb of charge gain. Okay, and we can calculate this amount of work done or this amount of energy by taking the potential difference between the cathode and the anode and multiply the amount of charge. So in this case, because the velocity that we want to calculate is 1 electron, the velocity of 1 electron. So this charge, okay, so this charge is the charge of 1 electron. So, for example, potential difference is work done per unit charge. So because the charge that we are talking about is the charge of 1 electron, so we can put the symbol of E to represent the amount of charge in 1 electron. Okay, so as you can see here, E is the charge of an electron. And then this W is the work done to move that 1 electron. And this W, this work done, will also equal to the energy that the electron gain. So we can substitute this W with the symbol of E to represent the electrical potential energy that acts on the electron. Okay, so this electrical potential energy actually means the potential difference Okay, the energy in potential difference between cathode and anode. Okay, electrical potential energy. So you can see why is it that it's called electrical potential energy, because you see the cathode is negatively charged and the anode is positively charged. So you can say that you can imagine like the cathode and the anode is like a slope like that. Okay, it's like a slope. Okay, it's like a slope. Okay, here is a cathode, here is an anode. So this is the electron. You see or not? So because it's a slope, so one side positive, one side negative, one side positive. So there is potential energy similar to elastic potential energy or gravitational potential energy like that. So the electron can move, okay, gain energy and move between the cathode and the anode. Okay, get the idea. All right, so the work done, we can substitute with, we can represent by electrical potential energy. And this amount of charge is the amount of charge of one electron. So the amount of energy that the electron gains can be calculated by taking the amount of charge of one electron multiplied by the potential difference between the cathode and the anode. Okay, all right. So this amount of energy, because it will convert into kinetic energy, so that means we can equal them lah. Okay, we can equal them. So that means this electron volt or this amount of energy from charge of electron multiplied by the potential difference can be equal to the kinetic energy. So we can equal them. So we can write EV equals to half mv squared. Okay. So with this information, that means if we have the charge of one electron, we know the potential difference between the cathode and the anode, and we know the mass of the electron. Then we can calculate the maximum velocity of the electron when the electron reach the anode. Okay, remember this is the velocity of the electron when it reach the anode, not when it's halfway. Because some students they misunderstood. They thought that after they calculate this velocity, they thought that from the starting from the cathode until the anode, the electron is moving in a uniform velocity. No, the electron accelerate from cathode until the anode. Okay, because at first the electron have zero kinetic energy. So when the electron is accelerating towards the anode, it's getting faster and faster. So meaning that energy is being transferred into the electron as kinetic energy. So the kinetic energy of the electron getting higher and higher and higher and higher. So the velocity will get faster and faster and faster. So when we reach the anode, then it will reach the maximum velocity. Okay, maximum velocity from the total amount of energy that it gained. Okay, get the idea. So this is also explained here. Okay, so applying the principle of conservation of energy, the electrical potential energy equal to the maximum potential energy. So we can write EV equals to half mv squared. So here it says, it's written that V max. Okay, V max, that means the maximum velocity. Okay, maximum velocity of the electron. Okay, so the charge of electron and the mass of the electron is a constant number. Okay, it's a fixed number. So that information will be provided. Okay, that means you do not have to memorize the charge of the electron is how much, the mass of the electron how much. You do not need to. Okay, if a question come out where ask you to calculate, then the question, either the question will provide you with this information, or this information will be written in the list of formula and constant number in front of the second page of the question paper lah. Okay, all right. So until here, anybody have any question? Any problem? Anybody have any problem? Any question? Okay, thank you very much for responding. Thank you very much. Okay. Okay, looks good. Today the number is about the same as yesterday. I think yesterday is 24. Today is 34. Today is 20. Actually, it's 33 lah. Okay, it's 33. So about the same. Okay, good, promising. Okay. All right. So thank you very much. All right. So when your people respond, I feel motivated lah. Okay, I feel motivated. Okay, thank you very much. Okay, so next, okay, let's look at an example. Okay, figure 5.5 show an electron beam that is accelerated from the cathode to the anode in a vacuum. The potential difference across the cathode and the anode is 550 volt. So given mass of electron and charge of electron. Okay, so the question or the diagram. Okay, is this one lah. Okay, this is the figure 5.5. So here is a cathode, here is an anode. So the electron accelerate, okay, between the cathode and the anode. So it shows here that the anode is connected to positive 550 volt. Here you see the cathode is connected to 0 volt lah. So actually this represent okay, for your information, I know that many of you do not know what does this mean. You see here is 0 volt, here is 550 volt. So that means the potential difference between them, between this point and this point, actually it's the same as this here, this point and this point because this cathode here is connected to 0. So and this anode is connected to 550. So that means the potential difference between these two, between the cathode and the anode here is 550 volt. Okay, that is what this means. Okay, that is what this means. All right. Okay, so A, what is the electrical potential energy of an electron? So you can calculate with the equation E equals to EV, energy equals to EV, or if you want, let's say if you don't want, you want to use the original equation. Potential difference equals to work over charge. You want to use this to calculate the energy, also can, no problem one. Okay, there is no rule that says, oh, you must use this equation. No, to use this to get this work done is how much is the same thing. Okay, it is the same thing. So since we learn this, we are learning this, so I will show the working using this equation. Okay, so the charge of an electron 1.6 times 10 power by negative 19, potential difference 550 volt. So you get okay, so every electron will get the energy of 8.8 times 10 power by negative 17 joule. Okay, 8.8 times 10 power by negative 17 joule, or Another unit that we can use is the unit of electron volt. Okay, this is called this is a unit of energy. Okay, we read as electron volt. Okay, electron volt. So this E represent the charge, amount of charge. This volt represent the unit of the potential difference, how many volt. Okay, so electron volt. So you want to write as joule also can, you want to write as electron volt also can. Okay, so the unit of electron volt we use to usually we use this unit when we are referring to amount of energy that is contained within one electron. Okay, within the charge of one electron. So when you use the unit of electron volt, when people see 8.8 times 10 power by negative 17 electron volt, oh, people immediately know that what we are talking about is the amount of energy that is inside one electron. Okay, so that is the context or how we apply, how we use the unit of electron volt. Okay, when you want to tell people that this unit is the amount of this energy is the amount of energy inside and inside one electron or inside the charge that is one electron. Okay, the charge is within one electron. All right. So, however, if you don't want, okay, you use joule is perfectly fine. Okay, perfectly fine. All right, but this unit is something that you need to know, okay? Although it's not not compulsory that you must use, but it's you need to know this unit, so that if like question give you, for example, if question give you information about the amount of energy, and then the question did tell you that this is energy of one electron, the person just tell you that give you the information, okay, how much electron volt. Then if you don't know this unit and then you see this unit electron volt, then you will get confused. You will not know what is this electron volt, what is this EV, what, okay, if you don't know. Then if you don't know, then you will not be able to know how to use that information. Okay, so B. Okay. B, what is the kinetic energy of an electron when it reaches the anode? Okay, so the kinetic energy is equal to 8.8 times 10 power by negative 17 joule. Okay, because this is the amount of energy that is gained by an electron, and that energy will be converted into kinetic energy. Okay, C, what is the maximum velocity of an electron when it reaches the anode? So, kinetic energy equals to half mv squared. So 8.8 times 10 power by negative 17 equals to half the mass of the electron, 9.11 times 10 power by negative 31 kilogram. Then velocity squared. So how much is the velocity? Okay, so the velocity would be 138,994.95 meter per second. Okay. Okay, 1.13899.434.95 meter per second. All right. So this is the maximum velocity of the electron. As you can see, the velocity is extremely high. Okay, the electron is moving at a very, very high velocity. Okay, so until here, then we finished the topic about in 5.1 about electron. Okay, so anybody have any question, any problem here? Okay, thank you very much. Thank you for responding. Okay, thank you for responding. Okay, so so as usual, please do all the objective questions. I will not discuss any of the structural questions lah. Okay, next time when we have time, okay, if we have time now, then we go and discuss. Okay, so let's continue to topic 5.2. Okay, please get ready. We want to continue with topic 5.2, which is about semiconductor diode. Okay, so today our class will be until 11:20. Wait until 11:20 only because people want to come. They come to also to finish earlier. Okay, so but my target is I want to finish up the semiconductor diode with this topic now. Okay, let's begin. Okay, 5.2 semiconductor diode. All right, so let's look at okay. So the first thing that we want to learn here is the function of a semiconductor diode. But of course, before that, we have to learn what is a semiconductor diode, and even before that, we need to learn how is it that the semiconductor diode function. How does it work? And in order to understand how does it work, we need to understand what is a semiconductor. So first, what is semiconductor? Semiconductors are material with resistance between that of conductor and insulator. Okay, or more precisely, it is a material with resistivity. Okay, the resistivity is between conductor and insulator lah. So if you look back, if you look back, you check back your note about when we learned about resistance, I think in topic 3.2, okay, about resistance, then there is a table. Okay, I got put a table that lists out the resistivity of conductors, of insulators, of semiconductors. So there in that table, you can see that the resistivity of conductors are in one group of their own. Semiconductor is in one group of their own, and and insulators are in another group of their own. So the resistivity are very far away from each other. Okay, so the resistivity of the conductors are very different from the resistivity of semiconductors, and they are also very different, very far away from the insulators. So they are in their own group like that. So this is why the resistance of semiconductors, conductors, insulators, they are very, very different. Okay, they are the difference are very large. Okay, so Why is it that semiconductors have resistance between conductors and insulators? The reason is because of their limited number of free and mobile charge carriers. So the charge carrier that we are talking about are electrons or holes. Okay, we know that electrons are charge carrier, but what are holes? Okay, that is later what we are going to see that. Okay, we are going to learn what are holes. Okay, so semiconductors have okay, mobile charge carrier. So meaning the electrons. Okay, electrons. Electrons is it? Electron is the one that can move around. Okay, the proton cannot move. Proton cannot move. So when uh, electrons are charge carrier, they carry charge. So when we apply potential difference on the electron, then the electron will gain energy and it will be able to flow. Okay. However, different material have different number of free electrons. So metals are generally good conductors because they have more free electrons compared to semiconductors, and semiconductors have more free electrons compared to insulators. Okay, so example of semiconductors are like silicon and germanium. So silicon and germanium, silicon are the largest, is the most common material that we use to make uh, electronic component. Okay. Wait. Okay, sorry, continue. Okay, so we say that semiconductors are not a very good conductor. They are semiconductor. They have very limited charge carrier. They have limited free electron. So if they have limited free electron, they are not a good conductor. Well, how is it that semiconductors can be used as electronic component? Because electronic component need to be able to conduct electricity right now. Electric current need to flow through them. So how is it that we can use semiconductor as electronic component if they cannot conduct electricity well right now? So the thing that we want to do here is to increase the conductivity of the semiconductor. That means we want to make the semiconductor become a good conductor. So how do we do that? We do a process that is called doping. So what is doping? Doping is mixing. Okay, doping is mixing a small amount of impurities into semiconductors to increase its number of charge carrier. So just now we say, oh, very limited free electron. So increase the free electron. Okay. So how do we increase the number of free electron? There are two ways that we can do that. The first, we call it the N-type doping. Okay, so what is N-type doping? Okay, so you see, we say that the semiconductor have limited charge carrier right now, so we limited its free electrons. So we increase the number of free electrons. So how? We dope a pentavalent atom, okay? Pentavalent atom. So, for example, phosphorus. Phosphorus has 5 electron valence. So that means it has 1 extra electron valence compared to silicon. Okay, it has 1 extra electron compared to silicon. So if that is the case, then if you dope or you mix the phosphorus atom in among the silicon atom, then the phosphorus atom that have extra 1 electron, that extra electron will be able to move through the silicon crystal lattice. It can move through among the silicon atom. Okay. Okay, wait a minute. I think I start from the beginning, okay, from the most basic one. Okay, I think I introduced the silicon first. Okay, so let's say that this is silicon. Okay, so you see silicon have only 4 electron valence. Okay, silicon have 4 electron valence. Okay, and because silicon have only 4 electron valence, so when the silicon atom arrange together, what happens is they would share the electron with each other. So for example, let's say that this is the red silicon. Let's say this is the red silicon. So this electron belong to the red silicon. This electron belong to the red silicon. This is the red silicon electron. This is the red silicon electron. And let's say that this is the blue silicon. And this is the blue. This is electron that belong to the blue silicon, blue silicon, blue silicon, blue silicon. Okay, and then let's say that this is also the blue silicon. Okay, so this electron is the blue silicon electron. Okay, blue, blue. Okay, and this is the red silicon. So this is a red electron. Okay, this is the blue silicon. So this is the blue electron. This is the blue silicon, blue electron. Okay, so you see okay, so you see every silicon have only 4 electron valence. Okay, every silicon have only 4 electron valence. So when they share 1 electron with another silicon atom next to them, then they will achieve stability lah. Okay, they have, then if like that, if they share with each other, then that means every single silicon atom will have 8 electron valence. Then they will become stable. And because they are very stable, okay, when they are like this, very stable, or you can say that every single electron have an owner, okay, have an owner. So what happens is when you apply potential difference, okay, for example, you connect power source. When you connect power source to the silicon, Okay, positive, negative. So this negative here, you want to push the electron. Here want to pull the electron. Okay, here attract electron. Here repel electron. And the electron move or not? Cannot. Okay, all of the electrons are occupied. Okay, all of the electrons belong to some silicon. So they cannot move lah, because in this case, this is what we say, it has limited number of free electrons. Okay, it has very limited number of free electrons, so current is very difficult to pass through lah. Okay, very difficult for electron to flow. Okay, however, if we dope, okay, if we dope the silicon with phosphorus atom, phosphorus have 5 electron valence. So what happened? Let's say that this phosphorus is the red color. Okay, let's say this phosphorus is red color. So this is the phosphorus electron, phosphorus electron, phosphorus electron, phosphorus electron, phosphorus electron. So you see the phosphorus has 5 electrons. 1, 2, 3, 4, 5. So the phosphorus share 1 electron with the silicon next to it and still have 1 extra electron. So you see, extra free electron. So this extra free electron, it can move through the crystal when you apply potential difference across the doped silicon. Okay, the silicon that is doped with phosphorus. You see or not? So of course this is not doped with only 1 phosphorus atom lah. Okay, let's say over here also got phosphorus, here also got phosphorus, okay, got phosphorus mixed together with the silicon. So that means the number of free electron in the semiconductor, in the silicon semiconductor increase. So when you apply potential difference, the electron can pass through them. Okay, the electron can pass through them, and the resistance of the silicon will decrease. Okay, like that. So that means the silicon become a good conductor. You see that? Okay, the silicon become a good conductor. So we call this N-type doping because it increase the amount of electron, and the electron is carry negative charge. So that's why we call it N-type doping. Okay, we dope it with extra negative charge. Okay, so we call it N-type doping. So this type of semiconductor that have undergo N-type doping, we call it N-type semiconductor. Sorry, okay. So sorry, I'll continue. All right. So this type of semiconductor that has undergone N-type doping, we call it N-type semiconductor. Okay, we call it N-type semiconductor. Okay. So next, another type of doping is we call it P-type doping. Okay, we call it P-type doping. So in this P-type doping, what we do is we dope with boron, gallium, or iridium into the silicon lattice to form holes. So how is it that it can form holes? Because boron, gallium, iridium, they are trivalent atoms. Okay, trivalent atoms. That means they have only 3 electron valence. Okay? They only have 3 electron valence. So for example, let's say this boron is red color. So the boron electron is this one, this one, this one. Okay? So oh wait, sorry. Okay. This is the boron electron, boron electron, boron electron. So this one is the silicon. So this is the electron that belong to this silicon. Okay, this is silicon. This is electron that belong to the silicon. This is silicon. This electron is the silicon one. This is silicon. This electron belong to the silicon. Okay, so you see the boron only have 3 electron valence. So that means here there is a hole missing or short with 1 electron. So this shortage of 1 electron, it forms what we call a positive hole, because the effect of shortage of electron is like you have a positive effect. That means it is like you have a positive charge. Okay, get the idea. I repeat, when you lack electron, the effect is that it's like you have extra positive charge. Okay, sorry, one more time. When you have shortage of electron, it is like you have extra proton, or you have extra positive charge. So this hole represents positive charge. Okay. However, when you put this semiconductor that doped with boron with potential difference, okay, for example, you apply, okay, you connect to power source. Okay, for example, like this, you connect to power source. So what happened is this. Wait, opposite. Okay, like this. Here is positive, here negative. So if I connect like this, what happens is this side, the positive side, it will attract electron. This negative terminal, it will repel electron. So what happens is the electron here will be repelled, and the electron will see, oh, in front here there's a hole. So this electron will jump here. So when the electron jump here, what will happen? Okay, when the electron jump here, what will happen? This will become the electron. The electron will be here, and then what will happen? This one become the positive hole. You see or not? Because when the electron jump here become missing electron. There's short of electron, and then continue. This electron can jump here, and then this one will become the electron, and then this one become the hole. You see or not? So the hole move here, and then continue. This electron can jump here, and then the hole, and then this one become the hole. Okay, this one become electron. So you see or not? When we apply potential difference onto the doped silicon, although the one that actually move is electron. I want to stress, the one that actually moving is electron. But you see the positive hole at first is here, right? But because the electron move, so the hole from here, move here, and move here. So you see, it makes it looks like the positive pole move from right to left, right now. Although physically, the one that actually move is electron, but it makes it looks like the positive pole is the one that is moving. Can see or not? So we take it, because of this, we take it that the positive pole is like a charge carrier, also a charge carrier that can move, and the charge that the hole carry is positive charge. Get the idea or not? Okay, so this is what we call a p-type doping. We call this the p-type doping because it increases the positive charge, or we dope the silicon with positive charge carrier. Okay, and this type of semiconductor, we call it the p-type semiconductor. Okay, all right. So so with doping, with n-type doping and p-type doping, we can increase the conductivity, or we can make the silicon or the semiconductor that is not a good conductor become a good conductor. Okay, I repeat that. Through doping, we change the semiconductor to become a good conductor. Okay, so until here, any question? Anybody have any question? Okay, no question. Thank you very much. Thank you for responding. Remember, the main thing that we want to understand here until here is how is it that what is a semiconductor, and how is it that we can change a semiconductor that is not a good conductor to become a good conductor. Okay, this is what we want to learn here. Okay, now continue. Wait. Okay, sorry, continue. Okay, now, next, what we want to see is how do we use the N-type semiconductor and the P-type semiconductor. You see, maybe some of you will think, what is the point of changing the semiconductor into good conductor? If we want good conductor, why not we just use copper or iron or aluminum? All of them have very low resistivity, and all of them are good conductor, right? Why go to all the trouble of changing the semiconductor into a good conductor for what? You see, just N-type semiconductor alone and P-type semiconductor alone, if they are separated, N-type semiconductor, P-type semiconductor separated, they do not have any special effect. Okay, there's nothing special about them. They are just a normal conductor only. If we separate the N-type and the P-type, however, something that is very special will happen when we combine them together. Okay, when we combine them together. Okay, so we look at here. Semiconductor diode is an electronic component which allows electric current to flow in one direction only. It is formed by joining a p-type semiconductor and an n-type semiconductor. The boundary between the p-type and n-type region is called the junction. At the p-n junction, electrons from the n side move to the p side and recombine with the hole. Hole from p side similarly move into the n side where they recombine with electron. As a result of this flow, the region around the junction is left with neither hole nor free electron. This region, depleted of charge carrier, is called the depletion layer and is a poor conductor of electricity. There is a potential difference between the N side and the P side. This potential difference is called the junction voltage. All right. So what do all of this means? Let's take a look at. Okay, so let's say that we have we have the semiconductor. Okay, we have the N-type semiconductor and the P-type semiconductor. We join them together. Okay, so this is the, let's say this is the N-type. This is the P-type. So the N-type have electron. Okay, have extra electron. N-type semiconductor have extra electron. And then the P-type semiconductor have holes. Okay, they have holes. Holes, that means they are lack of electron. Okay, now, what happens when we join them together, when we stick them together, is, okay, the boundary or the border between these two, we call it the junction. Okay, the junction or the PN junction. Okay, PN junction, because P-type and N-type connect together. So the PN junction. Okay, so what happened at the PN junction is when you stick them together, we see here have extra electron right now. Electron and electron, they will repel each other because negative charge repel each other. So this one is hole. Hole, we say that the holes are positive charge carrier. So in concept, positive and positive, they will repel each other. So that means the positive hole also can move lah. Okay, we just imagine, we take it that the hole can move. But we must remember that what is actually moving is the electron. The electron is the one that is actually moving. Okay, so what happens here is that when we join them together at the PN junction, this electron, what will happen? It will go here and fill in the hole. Because this one got extra electron, here got lack of electron. So the electron will go inside here, fill in the hole, fill in the hole, fill in the hole, fill in the hole, fill in the hole. So what happens when they fill in the hole? The hole will be filled with electron. So that means the silicon or the atom that is short of one electron will get electron and the hole will be filled up. So no more hole. With no more hole, that means no more positive carrier, positive charge carrier. And here, the electron move here already. So that means here will be lack of electron. So that means here will also will not have, okay, it will lose the negative charge carrier. So what happens is here near the area that is near the PN junction become lack of charge carrier. Okay, lack of charge carrier. So we call this region we call this region the depletion layer. Okay, so this layer there is no charge carrier. So we call this the depletion layer. Okay, so you see this depletion layer, it will form like a wall like that. It becomes like a wall that separates the N-type semiconductor and the P-type semiconductor. So when there is, because of this depletion layer also, all the other electrons here will not be able to continue to go to the P-type and fill in the hole. So that means only the area around the junction will have depletion layer. That means the depletion layer will not automatically spread to all over the semiconductor. That means the whole semiconductor will not become depletion layer. Only the area that is near the junction will become depletion layer. Okay? You can see now. Okay, so this is what will happen when the P-type and the N-type semiconductor join together. Okay, now, what will happen when we connect this N-type and P-type semiconductor to power source? Okay, so let's say here, this is negative, this is positive. Okay, we connect them. Okay, so what happened? This negative terminal, it will repel the electron right now. Okay, it will repel the electron. This one, the positive, it will attract the electron right now. Okay, one side repel electron, one side attract electron. So what happened is this electron, okay, it will repel electron. Repel the electron. So what happens is the electron will move towards the depletion layer. So what happens is it will be able to push the electron out of the hole. That means this one, it will push the electron out of the hole. Because the electron now have more energy already, got energy supply. So it will push. So this electron that sit in the hole will be able to jump out. Okay, will be able to jump out of the hole and move forward to the next hole. And then when this jump out, here got hole already, right now. So the other electron can go in. Okay, the other electron can go in. You see that? The electron can go in. So what happens is, that means inside here, there will be more charge carrier inside here. Okay, there will be more charge carrier inside here. So what happens is the depletion layer will become narrow. Okay, the depletion layer will become narrow. Okay, I think I need to explain in a little bit more detail about this part. Okay, let me start again. Sorry. Let me start again. Okay, so when we I think I need to explain about the junction voltage. Here got say about the junction voltage. Where there's a junction voltage. Okay, so you see because here have extra electron, here have a lack of electron. So that means here is negatively charged, metal is positively charged. So that means this situation, across the depletion layer is like there is electric potential energy. Understand that? It's like there is a potential difference across the depletion layer. Okay, get the idea. Because here positive charge, here negative charge. So you can imagine like the situation is similar like, okay, when you have two metal plate. So this metal plate is negatively charged. This metal plate is positively charged. So if you have two metal plate like that, so that means there will be potential difference between the two metal plate. Okay. So if the potential difference is strong enough, then the electron can jump lah. Okay, like that. But however, what I want to stress on here is that it is similar to like there is potential difference between these two metal plate, because one side is negatively charged, one side is positively charged. So you see here is similar. This side is negatively charged, this side is positively charged. So there is a voltage. Okay, there's potential difference. So there is voltage across the depletion layer or across the PN junction. So this voltage we call it a junction voltage. Okay, we call it a junction voltage. All right. However, you see this junction voltage. Let's say this junction voltage is 1 volt. Let's say for example, this junction voltage is, okay, let's say that this junction voltage is 1 volt, for example. So what happened is, if this power supply is 0.5 volt, that means it is lower than the junction voltage. What will happen is the 0.5 volt will be able to push the electron go nearer to the junction. Okay, and this positive will be able to pull some of the electron out. So that means here got hole, here got electron. So what happened is the depletion layer will become narrow. Okay, the depletion layer will become narrow. Okay, the depletion layer become narrow. Get the idea? Because this one, it can go against the junction voltage. This power source, it go against the junction voltage. So this one become narrow. It push. Here, although actually what happened is the electron is pulled out, but we can also say that this positive charge, it repel the hole, because remember the hole represents positive charge. So the positive terminal repel the hole, so the hole go towards the junction. Okay, so that means here got hole, here got electron, but so the depletion layer become narrow. So if we increase the power supply, the voltage of the power supply, so let's say become 0.9 volt, then the depletion layer will become even more narrow lah. Right? Okay, will become even more narrow. become very narrow. Okay, it will become very narrow. It will become even more narrow. Then like that. So what happens is when this power source is more than 1 volt or equal to 1 volt, equal to 1 volt or more than 1 volt, okay, let's say 1.1 volt, then this depletion layer will disappear. Okay, this depletion layer will disappear. Okay, the depletion layer will disappear, and the electron can flow through the junction, can pass through the junction because it has overcome the junction voltage. Okay, the power source has overcome the junction voltage, so the electron can flow through the PN junction. Can see enough? Okay, can flow through the PN junction. So if you put a bulb here, then this bulb will light up lah. This bulb will light up. Current can pass through. But of course, this one, the power source, it must be, the voltage of the power source must be higher than the junction voltage. Okay, it must be higher than the junction voltage, then the electron can pass through. So if the electron flow this direction, so that means, remember, the current will be in the opposite direction. This is the flow of electron. This is the flow of current. So the flow of hole, remember, the hole represents positive charge. So the hole flow in the opposite direction as the flow of electron. So the direction of flow of the hole is the same as the current. Okay? Okay? Alright. So what happens if we connect, or if we reverse the connection? What will happen? That means like this. If we reverse the connection. Okay, here we got electron. Okay, and here we got hole. Okay, so just like same like just now. Same like just now. Again, this is N pi. This is P pi. Okay, and when they join together, there will be depletion layer. Okay, join together, there will be depletion layer. Okay, depletion layer. And what happens if we reverse the connection? That means here is positive, here is negative. What will happen is this positive, it will attract the electron line. So the electron will move away from the junction. This negative, it will attract the hole. We just say that the hole represent like a positive charge. So positive charge can be attracted by the negative terminal. So the hole will be attracted by the negative terminal. But of course, what actually happened is the negative repel the electron. So the electron here negative push the electron. So the electron go inside here and fill in the hole. Okay, fill in the hole. So because the hole here become lack of hole, so it is like the hole is moving away from the junction. So over here, the electron move away from junction. Here, the hole move away from junction. So what happened is the depletion layer expand. Okay, depletion layer become wider. Okay, the depletion layer become wider. You see, okay, the depletion layer become wider. Depletion layer expand. So if the depletion layer expand, what does this mean? If you connect a bulb here, can the bulb light up or not? Cannot, the bulb cannot light up because the electron cannot pass through the junction. So there's no current. You see or not? There's no current. So what does this tell us? This shows us that this device that is constructed from N-type and P-type semiconductor only allow current to flow in one direction only. That means if you connect like this, negative to the N-type, positive to the P-type, then current can flow. If you connect in reverse, positive to the N-type, negative to the P-type, current cannot flow. You see that? Current cannot flow. So what we have here is a diode. Okay, because it's only allow current to flow in one direction only. So we call this a diode. And because this diode is made from semiconductor, so we call it a semiconductor diode. Okay? Or a PN junction semiconductor diode lah. Okay? Get the idea? Okay, so this is what we are talking. This is what is explained here lah. Formed by joining a p-type semiconductor, n-type semiconductor, boundary become is a junction, and the CN junction, the electron from n side move to the p side. All of that. This whole thing here is what I explained just now lah. Okay, all of this is explanation of this one. Okay, so you see when we combine the p-type semiconductor, n-type semiconductor, we get a semiconductor diode that only allow current to flow in one direction only. So the semiconductor diode can act like a valve. Okay, and can act like a valve to control the direction of the current. Okay, all right. So, but if person asks, what is the function of semiconductor diode, please do not say that it acts as a valve. Please do not say that it acts as a valve. We just say that it acts like a valve. Okay, it's like a valve, but it's actually not a valve lah. Okay, because a valve is a mechanical machine, but this is an electronic device. Okay, it's an electronic device. So if person asks What is the function of diode? You say it allow current to flow in one direction only. Okay, like that. So that is the function of semiconductor diode, to allow current to flow in one direction. Okay, can see now. Okay, now, so the connection that allow current to flow, we call it forward bias. The connection that do not allow current to flow, we call it reverse bias. Okay, so the symbol for the semiconductor diode is very simple. Okay, the symbol for semiconductor diode is an arrow. This arrow shows the direction of the flow of the current. And then you draw a line like this. So this line shows that current can flow this direction, but if you want to go in opposite direction, cannot. And join with power source. So if you join with power source like this, okay. Oh, sorry. I think I better follow this diagram. Okay, follow this diagram. The current can flow in this direction. Current cannot flow in the opposite direction. Okay, this is the current flow, positive to negative. Okay, so you connect like this. This is forward bias connection. Okay, this is forward bias. So this symbol is the electronic symbol of a diode. So this is forward bias. This one positive, so flow in this direction. So you see the arrow. So the current can flow in this direction. This side is negative. So if the current, if you reverse connection, or we connect reverse bias, for example, like this. So this is reverse bias. Okay, this is reverse bias. See, positive current want to go to negative, cannot. It's blocked here. Cannot. So this is the electronic symbol for the semiconductor diode. All right. So until here, any question? Anybody have any question until here? Okay, no question. Thank you very much. Okay, I know that the explanation is quite long because there are a lot of basic things that we need to establish. That means we need to make sure that you understand the basic structure of the silicon or the semiconductor, and then after that, how is it that we dope it to make it a good conductor, and then what will happen if we join them together? How do the electron move inside the N-type, P-type semiconductor? So there are a lot of things to explain, so that you get so you can understand how is it that the semiconductor diode function, how does it work? Okay, okay. So continue. Okay, now that we know how the semiconductor diode works, now we want to see how is it that we can apply. Okay, how is it that we can use it? We can apply for what? Okay, so this one is explanation. Okay, same explanation that what I explained just now. Okay, so for example here, okay, forward bias circuit. Okay, in the forward bias circuit, you have a thin depletion layer or there is no depletion layer. So when the diode is forward biased, the hole will move towards the N-type semiconductor, while electron will move towards P-type semiconductor. Depletion layer becomes thinner, junction voltage across the depletion layer decrease, and the resistance of the diode become very small. So here the junction voltage, we say that it decreased because the power source, okay, the power source overcome the junction voltage, okay, overcome the junction voltage. Okay, so the current pass through the diode, causing the bulb to light up. Okay, this one, when reverse bias circuit or reverse bias connection, when the diode is reverse biased, the hole and the electron will both move away from the depletion layer in opposite direction. So depletion layer becomes thicker, junction voltage across the depletion layer increase until we reach the potential difference of the battery. So the resistance of the diode become very high. Okay, so the current stop flowing and the bulb does not light up. Okay, so continue. The use of semiconductor diode. Okay, the use of semiconductor diode and capacitor in the rectification of alternating current. Okay, this is the application of the semiconductor diode. So the application here is we use the diode as a rectifier. So a rectifier is a device that can convert alternating current to direct current. So rectification is a process of converting an alternating current into direct current. So first, let's look at half-wave rectification. So half-wave rectification is like this. You see here, this is the alternating current power source. This is the load. Okay, so if you connect like this is the alternating current input right now. So this is one direction, and then in opposite direction, positive direction, negative direction. Okay, so these two is in the opposite direction. So that means that, let's say during the positive direction or the positive half cycle, it is this direction. That means it's forward bias. So that means when here is forward bias. So that means this part of the current can pass through. You see or not? So the current that pass through is only in this direction. But when the current change direction, want to flow in the opposite direction, the current cannot flow. Okay, the current cannot flow because it is reverse bias. Okay, this part is forward bias, this direction is reverse bias. So the reverse bias half cycle or the negative half cycle cannot pass through. So you see, the current that pass through the load, there is no negative half cycle, only the positive half cycle pass through. However, although it is like this, that means the current that the load receive is got current, no current, got current, no current, got current, no current, although like that, but the current that pass through is still in the same direction, right? Okay, still in the same direction. So we still call this a direct current. This is still considered a direct current. So that means the diode have convert the alternating current into direct current. You see or not? However, this is called the half wave rectification because it only convert half of the wave. Okay, only convert half of the wave. So is this good or not? Of course, this is not good. Why? Because it only allows half of the electrical energy to pass through only. I repeat, only half of the electrical energy can pass through the diode. The other half cannot pass through. So that means if this load is a bulb, If this is a bulb, then the bulb will be dim light, not bright. Understand? The bulb can still light up, but it's not bright. Okay, get the idea. Because only half of the energy can pass through. Okay, so this is half wave rectification. Okay, next we want to look at a better version of rectification, a better method. Is called the full wave rectification. Okay, so the full wave rectification is achieved through a bridge rectifier. This bridge rectifier is the arrangement of 4 diodes in this way. You see, 1 diode, 2 diode, 3 diode, 4 diode. So the diodes are arranged in this way, in this arrangement. So this arrangement of diode is called the bridge rectifier, okay, or the bridge rectifier circuit. Okay, so this looks like very complicated right now. However, we need to learn how to draw. Okay, the way to draw is actually very simple. You see, when we want to draw the bridge rectifier, we think like that. Number 1, we arrange the 4 diodes like in diamond shape. Okay? Okay, we arrange the 4 diodes. Okay? Like this. 1. Okay, here got 1, 2, and then 1, 2, 3, 4. Okay? Arranged in diamond shape. Okay? Number 2 is the arrangement of the diode is from left to right. That means it must arrange so that it looks like the current can flow from left to right. That means like this lah. Like this. Like this. So you see, the current can flow from left to right. Right. Okay, from left to right. Like this. Like this. Okay, the current can flow from left to right. You see? From left to right. And then after that, top, bottom, power source. That means here and here connect to the power supply, alternating current power supply. And then the number 4, left, right, load. Okay, left, right, go to the load. Like this. Okay, left, right, go to the load. So let's say this is a bulb now. Okay, like this. Okay, so this is the, it's like the mantra lah, when we want to draw the bridge rectifier. So first is arrange in diamond shape. Okay, diamond shape. Second, the diode left to right. The third, top, bottom, power source. Left, right, load. Okay, like that. So once you are familiar, it's actually quite simple lah. Okay, now we want to see how is it that the current can be converted into from alternating current convert into direct current. Okay, so we see Okay, top bottom, power source. Left, right. Is the load. Okay, now first, let's say that the because alternating current flow in two direction, right? Okay, so let's say at first is this side is positive, this side is negative lah. So the current flow this direction. Remember, the current want to go from positive to negative. So what happened is this is the starting point, this is the destination. So the current want to go here, want to go to the negative. So another way is you think like the positive is at the top of the mountain, the negative is at the bottom of the mountain. So the water want to flow from high place to low place. Okay, the water want to flow from high to low. Okay, remember water flow from high to low. So this positive is high, negative is lower. So positive, the current flow here got two choices, left or right. Of course, flow here lah. Why flow here? Why go to the right? Because here is reverse bias. You see or not? This is reverse bias, so cannot flow here. So the current flow here. Current reach here. Want to go left or right? Of course, go right lah. Because here is reverse bias. You see or not? This one reverse bias, so the current cannot go here. So this is reverse bias. Sorry. Okay, sorry, continue. Okay, so that means the current will flow here. Okay, in this direction. Okay, flow in this direction. And then the current will go here. And then you see here, got two choices, go up or down. Which one the current will go, up or down? Remember, the starting point is the positive. The ending point, the destination is negative. So the positive is the top of the mountain. The negative is the bottom of the mountain. Okay, it's a low place. So if the you see if the current go here, you see here is getting higher on right or not? If it go here, that means become nearer to the top, to the positive. So this positive push repel the positive charge. Okay, so that means the current cannot go up here lah. Because if go up here, this is like going against the height, go back to the top of the mountain like this. So that means the current go down here lah. Okay, go here. So that this one is near to the destination. Flow to the bottom. The water flow from high to low. So it flow down here. Got two choices. Which here got two choices. Go left or go right. Of course, go left. Because go left, reach the destination. Go downward. This one is go upward near to the positive. So it will not go here. The current will flow here. Reach the destination. So you see, this is how the current flow. Okay, this is how the current flow. Okay, now the this one, okay, flow here. So if we draw a graph, it will look like this. Or if we connect this, if we connect here, this point and this point, if we connect the cathode ray oscilloscope, okay, cathode ray oscilloscope, cathode ray oscilloscope, then the cathode ray oscilloscope will show the current that flow is like this, same like this graph. This is the voltage, this is the time, and then the graph will be like this. Okay, one direction. Okay. Okay, now that let's say that you want to go in the opposite direction, this one change direction, the alternating current change direction. That means now this one become positive, this one become negative. Right now. So what happens? This one is the high place, this one is the low place. So the current start from here, go here. You see got two choices, left or right. Of course, go to the right because here is reverse bias, cannot flow. So the current flow here until here got two choices, go up or down. Of course, it will go down because up here is reverse bias. So the current pass through the bulb and the cathode ray oscilloscope will show in the same direction also. You see, in the same side because you see same direction. You see or not? Here starting is opposite direction, but when reach the bulb or reach the load, it becomes the same direction. So that means alternating current change into direct current already. Okay, so flow here, pass through here, go here. Two choices, up or down. Okay, of course it will want to go up because this is the destination, right? Not? Okay, if go down here, that means near to the starting point. So the current will go up here, near to the destination, left or right, of course go left, reach the destination. Because here near to the destination, this one is near to the starting point. So you see or not? This is how the current flow, this is how the charge flow. Okay, how the current flow. So if continue, reverse again, then it will become like this. And then change direction again, become like this. So this is the graph that we can see appear on the cathode ray oscilloscope. Okay, like this. You see or not? So at first the input, if we connect here, if you connect here and here to cathode ray oscilloscope, then this cathode ray oscilloscope will show the graph that look like this. So the graph change from here, positive half cycle, negative half cycle, positive half cycle, negative half cycle, to become all the same direction. You see or not? This is a positive half cycle. This is supposed to be a negative half cycle, but change direction already. Become all the same direction. So this is direct current. Okay, this is alternating current change into direct current. So this is what we call the full wave rectification. Okay, this is the full wave rectification. Okay, full wave rectification. So this is better lah. This full wave rectification is of course better than the half wave rectification because it allows the all of the energy from the current, all energy of the alternating current to pass through the load. Okay, you see on that. Okay, you get all of the energy. So if we connect a bulb here, if this is a bulb, so this bulb will be brighter lah. This bulb will be brighter than just now the half wave rectification. Okay, get the idea. Okay, but is this the best? Is this the best way to rectify the alternating current? No, half wave, full wave rectification is still not the best. Okay, why is it not the best? Not good enough because you see the voltage become strong, become weak, become strong, become weak, become strong and weak and strong and weak. If you connect this kind of current, the current strong, weak, strong, weak, strong, weak, if you connect it to an electronic device, for example, you connect it to your handphone, you charge your handphone, charge your laptop, connect to your television and all of that. The electronic component in your television, in your handphone and so on, the circuit will get damaged very quickly because when the voltage decrease, that means the electronic component become hot and cold, hot and cold, hot and cold. So it can shorten the lifespan of the electronic device. So what is the best direct current? What is the best direct current? The best direct current is of course the direct current from battery, from dry cell. You see the direct current from dry cell, okay, direct current from dry cell or battery, the graph is a straight line. Right now, it's a complete straight line. If it is 1.5 volt, then it's 1.5 volt all the time. It will not become stronger and weaker, stronger, weaker, stronger, weaker. No, it constantly 1.5 volt all the time. So this is the best direct current that we want. So how is it that we can convert this type of direct current, unstable, up, down, up, down, up, down, to this kind of smooth direct current? So we connect an electronic component that is called the capacitor to the circuit. Okay? Connect a capacitor. Okay, we connect a capacitor in the to the half wave rectification or to the full wave rectification to help in smoothing the direct current. Smoothing, that means to make it smooth lah, to make the direct current smooth. Okay, so what is a capacitor actually? Okay, so the basic structure of the capacitor, okay, is basically like this. Okay, let's say that we have a power source. Okay, we have a power source. So here is a bulb. And then here is two metal plates. Okay, let's say there are two metal plates here. So this is positive, this is negative. So if this dry cell, this power source, let's say is 1.5 volt, what happens is this bulb will get 1.5 volt, so the bulb can turn on, okay, light up. But at the same time, these two metal plates will also get charged up. This will be charged, positively charged. This one will become negatively charged, right? And the potential difference between these two metal plates will also be the same, 1.5 volt. Okay, the potential difference between the two metal plates is also 1.5 volt. Okay, so the charge, the difference in charge between the positive plate and the negative plate produce a potential difference of 1.5 volt. Okay, now let's say that we disconnect this power source. If we disconnect this power source, what will happen? This bulb, it will not immediately turn off. I repeat, it will not suddenly off. What will happen is the bulb will slowly become dim and then only off. Slowly turn off, become dimmer and dimmer and then off lah. Why? Because when you disconnect, that means there is no more electromotive force that push the electron here and do not attract the electron away from this two plate. So what will happen is, you see this metal plate here, negative and negative, they will repel. So the electron will flow. You see or not? So the electron will flow from here to here. Because this plate is short of electron, this metal plate is extra electron, negatively charged. So the electron will flow from this metal plate to this metal plate. So if electron flow, that means you have current. Okay, that means you have current flow. You see or not? You have current flow. This is the flow of electron. This is the flow of current. So you see, the electron will flow from the negatively charged plate to the positively charged plate until both sides become balanced. Until the charge on both sides become balanced, then the electron will not be able to flow anymore. So that is why the bulb will not turn off immediately. The bulb will slowly become dimmer and dimmer and dimmer, then moving off. You see or not? Okay, get the idea. Okay, because why it slowly become dimmer and dimmer? Because as the electron flow from the negative plate to the positive plate, that means the potential difference, this 1.5 volt becomes smaller and smaller and smaller. Because the difference in the charge become smaller and smaller. Okay, the negatively charged plate become less and less negative charge. The positive charge become less and less positive charge. So the 1.5 volt becomes smaller and smaller and smaller until zero. When both sides become balanced, then the 1.5 volt between the two metal plates becomes zero. So no electron can flow anymore. So no more current. So the bulb become dimmer and dimmer and dimmer and then off. Like that. Okay, get the idea. So these two metal plates, this is the basic form of a capacitor. Okay, this is the basic form of a capacitor. Why? You see, the capacitor basically is a device that can store charge. Okay, you see, capacitor is related to the word capacity. That means you can fill in something in the capacitor. The capacitor can store things, have capacity. The capacitor have a capacity to keep, to store things. And in this case, the thing that it can store are the charges, electric charge. Okay, so capacitor store charge. And when the potential difference that charge up the capacitor is become weak or turn off, then the capacitor will be discharged. It will discharge and release the charge that is stored inside the capacitor. So what happened is, you see here, okay, for example, this one, half wave rectification out, half wave rectifier, half wave rectification. Okay, this one is the symbol for capacitor. This one C, capacitor here. So you see, when this alternating current go up, it would charge up the capacitor. The capacitor will be charged. But when the alternating current want to change direction, it will go down, right now. It will go down. When it go down, that means the potential difference that charge up the capacitor become weak. So what happened? The capacitor will release the charge. Okay? Or we say that the capacitor discharge. Okay? Again, when the alternating current go up, it would charge the capacitor. Okay? The capacitor is charging. It charge up the capacitor. So when the alternating current it go down to change direction, the capacitor will discharge. So when it discharge, you see the load, this R, the load, the potential difference or the voltage that the load get, it will not drop together with the alternating current, but it will drop slowly. It will slowly go down because the capacitor release the charge to support. So it will discharge slowly. But before finish discharge, the alternating current will finish change direction and want to change direction again. So the alternating current increase in voltage in the same direction, and then it will charge up the capacitor again. Okay, charge up the capacitor. So this the load, the voltage that the load get will not drop until zero. It drop until halfway and then support by the alternating current power source. And then when the power source, alternating current power source want to go down, the voltage it will be support by the capacitor. The capacitor discharge and support. So it go down slowly lah. So you see this voltage that the resistor or the load receive will be more smooth compared with without the capacitor. If don't have capacitor, the voltage that the load get go up and then down, drop down until zero. And then for some time, there's a period of time where the load do not get any energy, and then got energy some more, and then drop down, no energy for some time, no energy, and then got energy some more, and then no energy. You see or not? So this is much better lah. This is better than without the capacitor. So this is smoother lah. Okay, got smoothing effect. But of course, because this is half-wave rectification, so of course, even with capacitor, it is not very smooth lah. So we look at full wave rectification. You see, if you connect the capacitor here, parallel, okay, the capacitor must connect parallel with the load. Then you see the alternating current go up, it would charge the capacitor, and then when the alternating current want to go down, it will be supported by the capacitor. The capacitor will discharge. You see or not? The capacitor discharge here to here. Here to here, the capacitor discharge. And then before then, it discharge a little bit. The alternating current change direction already. Want to go up again. Want to go up already. You see or not? So you see this is smoother lah, this is better lah, more smooth right now, more smooth. Okay, almost the same like the direct current, almost the same lah, almost the same like direct current. Not exactly the same like direct current, but almost the same. Okay, and see or not? Okay, so let's say that this is not good enough lah. Okay, I want the graph, I want the voltage that the load get really nice, really beautiful, really smooth, like direct current, like the direct current from the battery or the drive cell. So how is it that what is it that we can do? What is it that we can do is we use a capacitor with a bigger capacitance. Capacitance is the capacity of the capacitor lah. Okay, capacitor with bigger capacitance will be able to store more charge. The bigger the capacitance, the larger the amount of charge that the capacitor can store. Okay. Okay, here it doesn't say. So if we want even more smoother, we use more. If we want more smooth, then we use capacitor with larger capacitance. Okay, capacitance with a larger capacitance. Okay, so the bigger the capacity of the bigger the capacitance of the capacitor, the more charge that it can store. Then even then when the capacitor discharge, the amount of charge will only go down a little bit only. That means the potential difference of the capacitor only decrease a little bit, a very small amount. So if the capacitance is big enough, then you will not even be able to see the voltage drop lah. You will not see the voltage go down when it is charged. Okay, of course you need a capacitor with a very big capacitance lah. Okay, get the idea. Okay, all right. So until here is the whole topic about the semiconductor diode. Okay, so sorry, not a lot of example or exercise that we can discuss here. So anybody have any question until here? Okay, no question. All right, thank you very much. Okay, so like what I said just now, today we have to finish early a bit lah. So we have to stop here. But again, you can go, please go and do all the objective questions, okay, for the semiconductor diode. If you have any question, can message me to ask. Okay, so thank you very much. That is it about today. That is it that we covered today lah. All right, thank you very much.